Chapter 2. If you want to move something, you apply force to it. You either push it or pull it. To move dishes on a tablecloth, you can move them by pulling on the tablecloth. Pull slowly, and they'll move slowly. But what if you pull the tablecloth very quickly? Quick enough so that the force of friction between the cloth and dishes is very small and very brief. When no net force acts on an object, no change in motion occurs. The object is in mechanical equilibrium. Galileo's work set the stage for Isaac Newton, who was born shortly after Galileo's death in 1642. By the time Newton was 23, he had developed his famous 3 laws of motion that completed the overthrow of the Aristotelian physics. These 3 laws first appeared in one of the most famous books of all time, Newton's Philosophiae Naturalis Principia Mathematica, often simply known as the Principia. The first law is a restatement of Galileo's concept of inertia. The second law relates acceleration to its cause, force. The third law is a law of action and reaction. Newton's 3 laws of motion are the foundation of present-day mechanics. It was Newton's laws that got humans to the moon. Aristotle was the most famous philosopher, scientist, and educator in ancient Greece. He was the son of a physician who personally served the king of Macedonia. He entered the Academy of Plato at age 17, where he worked and studied for 20 years until Plato's death. He then became the tutor of young Alexander the Great. 8 years later, he formed his own school. Aristotle made careful observations, collected specimens, and gathered together and classified almost all existing knowledge of the physical world. His systemic approach became the method from which Western science later arose. After his death, his voluminous notebooks were preserved in caves near his home and were later sold to the library at Alexandria. Scholarly activity came to a stop in most of Europe during the Dark Ages, and the works of Aristotle were forgotten and lost. Various texts were reintroduced to Europe during the 11th and 12th centuries and translated into Latin. The Church, the dominant political and cultural force in Western Europe, at first prohibited the works of Aristotle, but soon thereafter the Church accepted them and incorporated them into Christian doctrine. The idea that motion requires a force, a push, or a pull, goes back to the 4th century BC when the Greeks were developing scientific ideas. This was the time of Aristotle, the most famous Greek scientist. Aristotle classified motion into 2 kinds, natural motion and unnatural motion. Natural motion, Aristotle believed, occurred without force. For example, motions of the sun, moon, and other objects in the sky were considered natural. These celestial objects move continuously without the need for any force to push or pull them. He taught that natural motion on Earth was directed either up or down. He said, for example, that it was natural for a boulder to fall down towards Earth and a puff of smoke to rise in air. He believed that objects have resting places that they naturally seek. He went on to say that it was natural for heavy objects to fall faster than light objects. Unnatural motion, on the other hand, required forces such as pushes or pulls by people or animals. For example, the only way to get a cart moving across the ground was to push or pull on it. Unnatural motion requires force. Aristotle's ideas were taken as fact for nearly 2,000 years, but in the early 1500s, the Italian scientist Galileo demolished Aristotle's belief that heavy things fall faster than light things. Legend tells us that Galileo dropped a heavy object and a light object from the Leaning Tower of Pisa. He showed that except for the effects of air friction, objects of different weights fell to the ground at the same time. Galileo made another huge discovery. He showed that Aristotle was wrong about forces being necessary to keep objects moving. Galileo said that a force is required to start an object moving, but once moving, no force is required to keep it moving, except for the force needed to overcome friction. When friction is absent, a moving object does not need a force to keep it moving. Galileo found a simple and powerful way to test his revolutionary idea. He rolled balls along flat plane surfaces tilted at different angles. He noted that a ball rolling down an inclined plane picks up speed. Gravity increases the ball's speed. He also noticed the ball slows down when rolling up an inclined plane. Then gravity decreases the ball's speed. What about a ball rolling on a level surface? While a ball rolls on a level surface, it doesn't roll with nor against gravity. Galileo saw that a ball rolling on a smooth horizontal plane doesn't speed up and doesn't slow down. It has a constant speed. Galileo reasoned that a ball moving horizontally would move forever if friction were entirely absent. A ball would move itself. All objects show the same property of motion as the balls rolling on Galileo's planes. The tendency of things is to remain as they are. If moving, they tend to remain moving. If at rest, they tend to remain at rest. This property of objects is called inertia. Inertia isn't a kind of force, it's a property of matter to resist changes in motion. A ball rolling down the incline on the left tends to roll up to its initial height on the right. The ball must roll a greater distance as the angle of incline on the right is reduced. Galileo was born in Pisa, Italy in the same year as Shakespeare was born and Michelangelo died. He studied medicine at the University of Pisa and then changed to mathematics. He developed an early interest in motion and was soon at odds with others around him who held to Aristotelian ideas of falling bodies. He left Pisa to teach at the University of Padua and became an advocate of the new theory of the solar system advanced by the Polish astronomer Copernicus. Galileo did all his work before the advent of mechanical clocks. He timed some of his experiments with his pulse and others with the dripping of water drops. Einstein called Galileo the father of modern physics and modern science. He was one of the first to build a telescope, and he was the first to direct it to the nighttime sky. He discovered mountains on the moon and the moons of Jupiter. Because Galileo published his findings in Italian instead of Latin typically used by scholars, and because of the recent invention of the printing press, Galileo's ideas reached many people. He soon ran into disagreements with the church and was warned not to teach and not to hold Copernican views. He restrained himself publicly for nearly 15 years. Then Galileo defiantly published his observations and conclusions, which didn't agree with the church doctrine. The outcome was a trial in which he was found guilty, and he was forced to renounce his discoveries. By then, an old man broken in health and spirit, he was sentenced to perpetual house arrest. Nevertheless, Galileo completed his studies on motion, and his writings were smuggled from Italy and published in Holland. Earlier, he damaged his eyes looking at the sun through a telescope, which led to blindness at the age of 74. He died 4 years later. So just a concept check, see if you understand where we're at and where we're going with it. A ball rolling on a pool table slowly comes to a stop. How would Aristotle explain this behavior? How would Galileo explain it? And how would you explain it? Aristotle would probably say that the ball stops because it seeks its natural state of rest, whereas Galileo would probably say that friction overcomes the ball's natural tendency to continue rolling. Only you can answer how you would explain it. So the big contrast between Aristotle and Galileo is taking in mind friction. So Galileo's concept of speed and velocity. Before the time of Galileo, people described moving things as simply slow or fast. Such descriptions were vague. Galileo was the first to measure speed by considering the distance covered and the amount of time it takes. He defined speed as the distance covered per unit time. The word per means divided by. Speed equals distance divided by time. For example, if a horse covers 20 kilometers in an hour, or in a time of 1 hour, its speed is 20 kilometers per hour. Or if you run 6 meters in 1 second, your speed is 6 meters a second. These values are average speeds for the speed at any instant. Instantaneous speed may be different. Any combination of distance and time units can be used for speed. Kilometers per hour, which is centimeters per day, or whatever is useful and convenient. The slash symbol is read per. In science, the preferred unit of speed is meters per second. When we know both the speed and direction of an object, we know its velocity. For example, if a car travels at 60 kilometers an hour, we know its speed. But if we say it travels at 60 kilometers per hour to the north, we know its specific velocity. Speed is a description of how fast. Velocity is how fast and in what direction. A quantity such as velocity that specifies direction as well as magnitude is called a vector quantity. Constant speed means steady speed. Something with constant speed doesn't speed up or slow down. Constant velocity, on the other hand, means constant speed and constant direction. Constant direction is a straight line. The object's path doesn't curve. So constant velocity means motion in a straight line at a constant speed. In the next chapter, we will consider motion that is not constant, acceleration. The car on the circular track may have a constant speed, but its velocity is changing every instant. Why? The reason that the car's velocity is changing is because the car is not headed in the same direction. Even though it is traveling at the same constant speed, it does not have a constant direction. Therefore, it doesn't have a constant velocity. So what is the average speed of a cheetah that sprints 100 meters in 4 seconds? How about if it sprints 50 meters in 2 seconds? Remember that the formula for speed is average speed equals the distance covered divided by the time interval. Therefore, 100 meters divided by 4 seconds is 25 meters per second. Well, if it was 50 meters in 2 seconds, then it will be 50 meters divided by 2 seconds. Also, 25 meters per second. The speedometer on a bicycle moving east reads 50 kilometers per hour. It passes another bicycle moving west at 50 kilometers per hour. Do both bikes have the same speed? Do they have the same velocity? Both bicycles have the same speed, but they have opposite velocities because they are moving in opposite directions. Number 3. The bird flies at a constant speed in a constant direction. Say the same sentence in fewer words. So what is this sentence saying? So if a bird is flying at a constant speed, we know that the speed then, and in a constant direction. So when you have speed and direction, you have velocity. So the bird flies at a constant velocity. What is meant by relative motion? When you sit on a chair, your speed is 0 relative to the earth, but 30 kilometers per second relative to the sun. Everything is always moving. Even when you think you're standing still, you're actually speeding through space. You're moving relative to the sun and stars, though you are at rest relative to the earth. Right now, your speed relative to the sun is about 1,000 kilometers per hour, and you're moving even faster relative to the center of our galaxy. When discussing motion, we mean relative motion, motion relative to something else. When we say a space shuttle moves 30,000 kilometers per hour, we mean relative to Earth below. When we say a racing car reaches a speed of 300 kilometers per hour, we mean relative to the track. Unless stated otherwise, all speeds are relative to the surface of Earth. Motion is relative. Aristotle used logic to establish his ideas of motion. Galileo used experiment. Galileo showed that experiments are better than logic in testing knowledge. Galileo was concerned with how things move rather than why they move. The path was clear for Isaac Newton to make further connections on concepts of motion.
Larry Bassett from Thornwood, New York, asks, if you could meet and talk with any scientist who's ever lived, who would it be and why?
Isaac Newton. Isaac Newton.
Why?
No question about it. Isaac Newton. The smartest person ever to walk the face of this earth. Now, there are always these Newton versus Einstein battles that people have. Newton is high and Einstein is high, but Newton is higher. And they're both high compared to everybody else. Let's make that clear. Newton, you read his writings. The man was connected to the universe in spooky ways. The hair stands up on the back of my neck when I read the questions that he asked. We think of science as discovery. But before you make a discovery, you have to pose a question. And the most successful scientists in the history of the world are those who pose the right questions. Suppose your question had been, what kind of cheese is the moon made of? How far is that going to get you? If you start designing experiments to test for blue cheese and Parmesan Reggiano and Manchego, and you find out it's none of those cheeses because it's not made of cheese to begin with, okay? The question has to be the right question.
Right.
Just because you can put nouns and verbs in the right sequence doesn't make it the right question for the universe. If I ask you, at what temperature does the number 7 melt? What's the square root of a pork chop? These are meaningless questions. Maybe philosophers would run with them, but they're scientifically meaningless. Abandon them, go on to the next problem. Newton, his questions, reached into the soul of the universe, and he pulled out insights and wisdom that transformed our understanding of our place in the cosmos. He basically birthed the entire Industrial Revolution with the physics that enabled us to understand matter and motion, led to the understanding of energy, which was the foundations of the Industrial Revolution. Isaac Newton. I think about it all the time. What would I bring back in time to show him? Or if he came into modern times, what would I show him first? How much time would I, what would I line up to introduce him to? I'd show him a calculator, show him that we can now calculate things. I'd show him a computer. I'd show him an automobile, a horse-drawn carriage without a horse. Right? What else would you think that was?
Right.
If you'd only ever seen it. I'd tell him about relativity, that his work was expanded upon by someone who's brilliant that came after him.
You think he could understand relativity?
Can Newton understand relativity? the extensions of his work. That's what it is. The extensions. He'd have to learn some more mathematics. Okay? He'd have to learn some more math that hadn't yet been invented. So you say, well, will that be hard for him? No. Why? Because he invented calculus practically on a dare. Somebody said, Ike, why is it that planets orbit in the shape you call ellipses rather than circles? Why that shape? And he says, I'll get back to you on that. I'll get back to you. Goes away for a few months, come back. Here's the answer. Here's the answer. Here's why gravity produces ellipses for orbits. The guy said, well, how did you figure that out? Well, I had to invent this new kind of mathematics to do it. He invented calculus. Most of us sweat through it for multiple years in school just to learn it. He invented it practically on a dare. You asking me if he can learn relativity?
I'm convinced. I don't know why I ever doubted him.
So, not only everything I just told you, but Isaac Newton He discovered the laws of motion, the laws of gravity, the laws of optics. Then he turned 26. Okay?
I'm with you.
You want to fight about who the smartest person ever was? You know, I think we have a case here for Isaac Newton. Now, by the way, Einstein came up with relativity by the time he was 26. But he didn't invent a whole new system of mathematics in tandem with it, the way Newton did, having invented calculus before he turned 26. So, he's my man. I have a statue of him over there. That's Isaac Newton.
Oh.
And I own everything he's ever written.
At the age of 24, Isaac Newton extended Galileo's concept of inertia and gave it the status of a fundamental law that underlies all motion. He developed two other laws of motion as well. Newton's laws were influenced by Galileo's findings. Once and for all, they put to rest mistaken Aristotelian ideas that dominated the thinking of the best minds during the previous 2,000 years. So why isn't inertia a kind of force? Newton's first law of motion, usually called the law of inertia. You can think of inertia as another word for laziness or resistance to change. Every object continues in a state of rest or of uniform speed in a straight line unless acted on by a non-zero force. The key word in this law is an object continues to do whatever it happens to be doing unless a force is exerted upon it. If the object is at rest, it continues in a state of rest. This is nicely demonstrated when a tablecloth is skillfully whipped from beneath dishes sitting on a tabletop, leaving the dishes in their initial state of rest. On the other hand, if an object is moving, it continues to move without changing its speed or direction, as evidenced by space probes that continue to move in outer space. While the ancients thought continual forces were needed to maintain motion, the law of inertia proves a completely different way of thinking about motion. We now know that objects continue to move by themselves. If an object is at rest, you will have to apply force to get it moving. But once in motion, no force is needed except that to overcome any friction. The object moves in a straight line indefinitely.
Now I want you to make a prediction. In my left hand, I have a standard-sized basketball, and in my right hand, a 5-kilogram medicine ball. If I drop them both at exactly the same time, which one will hit the ground first?
This is a trick one, isn't it?
The heavy will go down first.
Well, yeah, it'll drop faster. They'll both hit the ground at the same time.
Give me a prediction.
I actually would have thought this one would go faster because it's heavier. Maybe it's that one. Maybe this one, yeah.
So you reckon this will be faster?
I reckon that one will be faster.
So why does that make it go faster?
Because the weight pulls it down quicker.
What are we measuring when we say, oh, it's heavier? What are we feeling?
Gravity?
Gravity.
Go ahead. Yeah, that's... Ooh.
Objects being pulled to the earth, I guess.
Okay, so which of these objects is being more pulled to the earth?
This one.
That one, the black one.
All right. Well, here's what we're going to do. I want you to hold both of those above your head. Can you get them really high? Can you? Okay, on the count of 3. Ready? 3, 2, 1.
Yeah! Exactly the same.
Oh, they fell at the same time. Exactly the same time.
They hit at the same time.
Was that what you expected to see?
No.
So what do you make of that?
I need to go read more books.
Magic?
Gravity is going to pull at the same rate, no matter how heavy or how light it is.
But gravity is how light or how heavy something is.
It's one big, massive mind.
There must be some force that's dragging them down, and actually the actual weight of it doesn't matter.
Something to do with mass or something.
I can't remember why.
It's almost like the weight holds it back in a way, even though that doesn't seem to make sense.
I think you might be hitting on an interesting point there. Weight holds it back. Now, it's not actually weight that holds it back, but inertia. That's the tendency of matter to maintain its state of motion, so to remain at rest if stationary, or to continue with constant velocity when in motion.
What's the big idea?
The big idea is this one has more mass, so it's got more weight, which you can clearly feel, but it's also got more inertia, which means it's also more sluggish.
Right.
It tends to resist acceleration. So that greater force is required to accelerate it at the same rate as this ball.
Like a heavy car trying to accelerate.
Like a heavy car trying to accelerate, you need more force to get it going.
Yeah.
Exactly. So what does all that mean? Well, the force on the medicine ball is greater than the force on the basketball, but it has more inertia. And what's really important is that the ratio of force to inertia is the same for all objects. So everything accelerates at the same rate and lands at the same time.
When a space shuttle travels in a nearly circular orbit around Earth, is a force required to maintain its high speed. If suddenly the force of gravity were cut off, what type of path would the shuttle follow? So no force in the direction of the shuttle's motion exists. The shuttle coasts by its own inertia. The only force acting on it is the force of gravity, which acts at right angles to its motion or towards the Earth's center. We'll see later that this right-angled force holds the shuttle in a circular path. If it were cut off, the shuttle would move in a straight line path at constant speed or constant velocity, because it has a certain direction and a certain speed. So the moving Earth. Can the bird drop down and catch a worm if the Earth moves at 30 kilometers per second? Well, we all know that birds catch worms when they're in trees. The 16th century Polish astronomer Copernicus caused great controversy when he published a book proposing that Earth revolves around the sun. This idea conflicted with the popular view that Earth was the center of the universe. Copernicus's concept of a sun-centered solar system was a result of years of studying the motion of the planets. He had kept his theory from the public for two reasons. The first reason was that he feared persecution. A theory so completely different from common opinion would surely be taken as an attack on established order. The second reason was reservations about it himself. He could not reconcile the idea of a moving Earth with the prevailing ideas of motion. The concept of inertia was unknown to him and others of his time. In the final days of his life, at the urging of close friends, he sent his manuscript De Revolutionibus Orbium Caelestium to the printer. The first copy of his famous exposition reached him on the day he died, May 24th, 1543. The idea of a moving Earth was much debated. Europeans thought, like Aristotle, that the existence of a force big enough to keep Earth moving was beyond their imagination. They had no idea of the concept of inertia. One of the arguments against a moving Earth was the following. Consider a bird sitting at rest on a branch of a tall tree. On the ground below is a fat, juicy worm. The bird sees the worm and drops vertically below and catches it. It was argued that this would be impossible if Earth were moving. A moving Earth would have to travel at an enormous speed to circle the sun in 1 year. While the bird would be in the air descending from its branch to the ground below, the worm would be swept far away along with the moving Earth. It seems that catching a worm on a moving Earth would be an impossible task. The fact that birds do catch worms from tree branches seemed to be clear evidence that Earth must be at rest. Can you see the error in this argument? Well, one way to look at this is, yes, the bird is moving, but so is the worm. The concept of inertia is missing. You see, not only is Earth moving at a great speed, but so are the tree, the branch of the tree, the bird that sits on it, the worm below, and even the air in between. Things in motion remain in motion if no unbalanced forces are acting upon them. So when the bird drops from the branch, its initial sideways motion remains unchanged. We live on a moving Earth. If you stand next to a wall and jump up so that your feet are no longer in contact with the floor, does the moving wall slam into you? Why not? It doesn't, because you are also traveling at the same speed before, during, and after your jump. The speed of Earth relative to the sun is not the speed of the wall relative to you. 400 years ago, people had difficulty with ideas like these. One reason is that they didn't yet travel in high-speed vehicles. Rather, they experienced slow, bumpy rides in horse-drawn carts. People were less aware of the effects of inertia. Today, we flip a coin in a high-speed car, bus, or plane, and catch the vertically moving coin as we would if the vehicle were at rest. We see evidence for the law of inertia when the horizontal motion of the coin before, during, and after the catch is the same. The coin always keeps up with us. So what exactly changes an object's state of motion? So we see that without force, objects don't speed up, slow down, or change direction. When we say force, we mean total force or net force acting on an object. Often more than one force acts. For example, when you throw a basketball, the force of gravity, air friction, and the pushing force you apply with your muscles all act on the ball. The net force on the ball is the combination of all of these forces. It is the net force that changes an object's state of motion. For example, suppose you pull in a box of chocolate bars with a force of 5 pounds. If your friend also pulls with 5 pounds in the same direction, the net force of the box is 10 pounds. If your friend pulls on the box with the same force as you, but in the opposite direction, the net force is 0. Now, if you increase your pull to 10 pounds and your friend pulls oppositely with 5 pounds, the net force is 5 pounds in the direction of your pull. In this illustration, instead of pounds, the scientific unit of force is used, the Newton, abbreviated with a capital N. Forces are shown by arrows. Arrows are used because forces are vector quantities. As mentioned earlier, a vector quantity has both magnitude, how much, and direction, which way. When an arrow represents a vector quantity, the arrow's length represents magnitude, and its direction shows the direction of the quantity. Such an arrow is called a vector. Suppose you tie a string around a 2-pound bag of sugar and hang it on a weighing scale similar to the scales found in grocery stores. A spring in the scale stretches until the scale reads 2 pounds. The stretched spring experiences a stretching force called tension. The same scale in a science lab is likely in units of newtons. This scale will show the weight of the bag of sugar as 9 newtons rather than 2 pounds. Both pounds and newtons are units of weight. Units of weight, in turn, are units of force. The bag of sugar is attracted to Earth with a gravitational force of 2 pounds, or equivalently 9 newtons. Hang twice as much sugar from the scale, and the reading will be 18 newtons. Note that there are 2 forces acting on the bag of sugar. Tension force acting upward, and weight acting downward. The 2 forces on the bag are equal and opposite and cancel to 0. Hence, the bag remains at rest. We say it is in mechanical equilibrium. Mechanical equilibrium is a state wherein no physical changes occur. It is a state of steadiness. When the net force of an object is 0, the object is said to be mechanically equal. This is known as the equilibrium rule. We express the equilibrium rule mathematically as EF equals 0. The symbol E stands for the vector sum of. The F stands for forces. Please don't be intimidated if the expression EF equals 0, which is physics shorthand that says a lot in a little space, that all forces acting on something add vectorially to 0. For a suspended object at rest, like the bag of sugar mentioned earlier, the rule states the forces acting upward on the object must be balanced by other forces acting downward to make the vector sum equal 0. Vector quantities take direction into account, so if upward forces are positive, downward ones are negative, and when summed, they equal 0. In this illustration, we see the forces of interest to Burl and Paul on their sign painting scaffold. The sum of the upward tensions is equal to the sum of their weights plus the weight of the scaffold. Notice how the magnitudes of the 2 upward vectors equal the magnitudes of the 3 downward vectors. Net force on the scaffold is 0. The scaffold is in mechanical equilibrium. So in this instance, you see the 2 gentlemen on the scaffold. The scaffold is held up by ropes. These ropes are pulling the upward tension, whereas the weight of the gentlemen and their buckets is feeling the downward tension. To be in mechanical equilibrium, these two tensions must be equal. So consider the gymnast hanging from the rings. If she hangs with her weight evenly divided between the two rings, how would scale readings in both supporting ropes compare with her weight? The reading on each scale will be half her weight. The sum of the readings on both scales then equals her weight. Suppose she hangs with slightly more of her weight supported by the left ring. How would a scale on the right read? When more of her weight is supported by the left ring, the reading on the right is less than half her weight. No matter how she hangs, the sum of the scale reading equals her weight. For example, if one scale reads 2/3 her weight, the other scale will read 1/3 her weight. Get it? For an object to rest on a horizontal surface, what is the support force equal to? Consider a book lying at rest on a desk. It is in equilibrium. What forces act on the book? One is the force due to gravity, the weight of the book. Since the book is in equilibrium, there must be another force acting on it to produce a net force of 0, an upward force opposite the force of gravity. Where is the upward force coming from? It is coming from the desk that supports the book. We call this the support force, the upward force that balances the weight of an object on a surface. A support force is often called the normal force. For an object at rest on a horizontal surface, the support force must equal the object's weight. So in this case, the support force must equal the weight of the book. We say the upward support force is positive and the downward weight is negative. The two forces add mathematically to 0, so the net force on the book is 0. Another way to say the same thing is pi f equals 0. To better understand that the desk pushes up on the book, think about a spring being compressed. If you push the spring down, you can feel the spring pushing upward on your hand. Similarly, the book lying on the desk compresses atoms in the desk, which behave like tiny springs. The weight of the book squeezes downward on the atoms, and the atoms push upward on the book. In this way, the compressed atoms produce the support force. When you step on a bathroom scale, two forces act on the scale. One force is the downward pull of gravity, your weight, and the other force is the upward support force of the floor. These forces compress a mechanism, in effect, a spring, that is calibrated to show your weight. So the scale shows the support force. When standing on a bathroom scale at rest, the amount of support force and the amount of your weight is equal. We say that they have the same magnitude. So what is the net force on a bathroom scale when a 110-pound person stands on it? 0. For the scale remains at rest. The scale reads support force, which has the same magnitude as weight, not the net force. Net force is going to take into other accounts of force. Suppose you stand on two bathroom scales with your weight evenly distributed between the two scales. What will each scale read? How about if you lean to put more of your weight on one scale than the other? The reading on each scale is half your weight. If you put more of your weight on one scale than the other, more than half your weight will be read on that scale, but less on the other. And this way, they add up to your weight. Like the example of the gymnast hanging by the rings. If one scale reads 2/3 her weight, the other scale will read 1/3 her weight. When an object isn't moving, it's in equilibrium. The forces on it add up to 0, but the state of rest is only one form of equilibrium. An object moving at constant speed in a straight line path is also equilibrium. We say the same thing when we say an object moving at constant velocity is in equilibrium. The forces on the object are also 0, in accordance with Newton's first law. Equilibrium is a state of no change. A bowling ball rolling at constant velocity is in equilibrium until it hits the pins. Whether at rest or steady rolling in a straight line path, The sum of the forces on the bowling ball is 0. It follows from Newton's first law that an object under the influence of only one force cannot be in equilibrium. Net force couldn't be 0 in such a case. Only when there is no force at all, or two or more forces combining to 0, can an object be in equilibrium. We can test whether or not something is in equilibrium by noting whether or not it undergoes changes in motion. Consider a crate of canned food being pushed horizontally across a storeroom floor. If it moves at constant velocity, it is in equilibrium. This tells us that more than one force is acting on the crate. Likely the force is the friction between the crate and the floor. The fact that the net force on the crate equals 0 means that the force of friction must be equal in magnitude and opposite in direction to our pushing force. Objects at rest are said to be in static equilibrium. Objects moving at constant velocity are said to be in dynamic equilibrium. Both of these situations are examples of mechanical equilibrium. There are other types of equilibrium. For example, when we study heat, we'll talk about thermal equilibrium, where temperature doesn't change. For rotational motion, there is rotational equilibrium. So an airplane flies at constant velocity. In other words, it is in dynamic equilibrium. Two horizontal forces push and act on the plane. One is the thrust of the propeller that pushes it forward. The other is the force of air resistance or drag that acts in the opposite direction. Which force is greater? Both forces have the same magnitude. Call the forward force exerted by the propeller positive. Then the air resistance is negative. Since the plane is in equilibrium, can you see that the two forces combine to equal 0? Calculate Emily's average walking speed when she covers 1 meter in 0.5 seconds. So the average speed equals the total distance covered divided by time. So 1 meter divided by 0.5 seconds is 2 meters per second. Here's another one. Aristotle distinguished between natural motion and unnatural motion. Galileo stated that all motion is natural, is unnatural, follows the same laws, or is an illusion. Galileo stated that all motion follows the same laws. The difference between speed and velocity most involves direction, amount, different units, or acceleration. Direction. The first scientist to discover the concept of inertia was Aristotle, Galileo, Newton, or Einstein. Galileo. According to Newton's first law of motion, objects at rest often remain at rest. Objects in motion tend to remain in motion. Both of these, or none of these. Both. Objects at rest tend to remain at rest, and objects in motion tend to remain in motion. A ball rolling along a bowling alley moves at constant speed, without the need of horizontal force, due to the slight force in its direction of motion, due to slight friction that slows it, or due to gravity. The ball rolling moves at constant speed without the need of a horizontal force. If your textbook is pulled to the right with 8 newtons while being pulled to the left with 5 newtons, the net force of this book is, well, none of these. Your textbook would be pulled 3 newtons to the right, 8 newtons one way and 5 newtons the other, with a net gain to the right of 3 newtons. The equilibrium rule, EF equals 0, applies to objects or systems at rest, objects or systems in uniform motion in a straight line, both of these, or none of these. Both of these. When you stand on 2 bathroom scales, 1 foot on each scale, with weight equally distributed, each scale will read your weight, half your weight, 0, or actually more than you weigh. They will read half your weight. If you push your desk along the floor with the force of 80 newtons and it slides at a constant speed, then the force of friction acting on the desk is also 80 newtons in the direction you push. 80 newtons in the opposite direction that you're pushing, 0, or none of these. The force of friction is acting 80 newtons in the direction opposite to your push. Suppose you stand on the floor of a train moving at constant speed in a straight line. If you jump straight upward, you will land at your original location, slightly in front of your original location, slightly in back of your original location, in back of your original location, at a distance, depends on how high you jump. You will land at your original location.